Rahim. Donc on assiste aujourd'hui à la soutenance du doctorat du candidat M. مرابطي Amar, dont le titre est Application de la méthode de décomposition en mode variationnel pour le diagnostic des défauts des machines tournantes. M. مرابطي, vous avez entre 30 et 35 minutes pour nous présenter l'essentiel de votre travail.
Thank you, Mr. President. First of all, I would like to start by thanking the jury member for accepting the attendance of this discussion. The distinguished members of the jury, my dear friends and family present today, it is with great honor that I present to you the culmination of my research thesis entitled Application of Variational Mode Decomposition in Sharp VMD for Fault Diagnosis in Rotating Machines. This presentation was structured in a way to be concise and precise, starting off with an introduction and problematic, followed by a comparative study between variational mode decomposition and empirical mode decomposition. Next, we have an optimization of mode number in VMD. Next, a combination of VMD with wavelet multi-resolutional analysis, and an automatization of fault detection using VMD and long shared-term memory neural networks. Finally, a general conclusion and perspectives. Starting off with an introduction and problematic, in an industrial context where global competition imposes increased demand on real-time monitoring, early failure detection, timely interventions, resource optimization, and improved equipment availability, rise the condition-based maintenance as a solution for optimizing all of the above. One of the key tools in condition-based maintenance is vibratory analysis. It is consistent with measuring vibration signals from inspected systems, followed by a study using different algorithms to identify defects, where we can monitor and diagnose to make decisions for maintenance. Vibration-based fault diagnosis in rotating machinery consists mainly of 4 different families, starting off with time domain methods, where we have mainly scalar indicators, followed by frequency domain methods such as spectrum analysis and cepstrum analysis. After that, we have time frequency domain methods such as wavelet transform, EMD analysis, VMD analysis, and so on. And finally, rise and advanced diagnostic methods that uses AI algorithms such as convolutional neural networks and support vector machine. These techniques are widely used to diagnose different defects in rotating machinery, such as shaft faults, bearing faults, gear faults, and belt faults. Moving on to the main objective of this thesis, which is enhancing fault diagnosis in rotating machinery through the use of signal processing method with a specific concentration of VMD, and the comparison of the results with other methods, and the optimization of the VMD method itself. So the main issue studied in this study can be subdivided into 4 main pillars: VMD versus EMD comparison, a VMD optimization, a wavelet multi-resolution analysis integration, and long shared-term memory implementation. Starting off with the comparative study between VMD and EMD, this chart summarizes the comparative study based on bibliographic research, where we have on the left side the advantages of EMD, and on the right side the advantages of VMD. We can see that EMD surpasses VMD concerning processing of nonlinear and non-stationary signals, locality, stopping criteria, and computational complexity, while VMD improved parameter specification, adaptivity, noise robustness, and mode mixing. As for the applications, both methods are widely applied for different faults and different scenarios. So here, the stopping criterion plays a crucial role for determining which method is best, which we shall see together in the proceed sections. As for the algorithm for both methods, we here illustrate the steps for both EMD and VMD process, where we see that the EMD is a direct decomposition technique using envelope maximas extremities, and the VMD method uses an optimization criterion to determine the intrinsic mode functions. The analytical description of both methods is described in equations shown in the slide. From 1 to 4, we can see that the EMD is a direct and more easy to obtain the EMFs, while VMD needs a strong mathematical background. Moving on to emphasize on the comparison between the two approaches, a test bench was used to obtain signals to see which method would perform better. The test bench used is a machine fault simulator, or MFS, that contains an electric motor, a transmission belt, and a one-stage gear. The gearbox contained two types of defects, a half-extracted tooth and a fully extracted tooth, with the characteristics shown in the table. The input frequency, the transmission ratio for the belt and the gear, the rotation frequency and the gear of the gear, and the meshing frequency of the gear. Two signals were chosen for this study. The main cause of choosing the signals is the comparison and not the fault detection itself. Starting off with an EMD analysis, the EMD method resulted in 14 EMFs as shown in figure 2, and the corresponding envelope spectrum is shown as well. A quick analysis of the scalar indicators of these 14 EMFs show that the first 4 EMFs are corresponding with the fault detection in the specific signal. So these 4 EMFs will furthermore analyzed using an envelope spectrum to obtain the figure 3. As we can see, there is no clear diagnosis of the half-extracted fault. This is due to the lack of, due to the presence of the impact of the tooth, and it was not harmed due to half extraction of one tooth. Moving on to the second case of the fully extracted tooth, in the same way, the first 4 EMFs of the resultant EMD EMFs were chosen to be analyzed using envelope spectra. The results are shown, and as clearly shown, we can see the harmonics of the rotation frequency of the input shaft, which has the defective gear. Moving on to the VMD analysis, in contrast to EMD, the VMD analysis needs a determination of number of modes. In this case, 14 EMFs were chosen consistent with EMD, as shown in figure 5, as well as the corresponding spectrum. In the same way, an analysis of the scalar indicators for these 14 EMFs show incoherent consistency contrast to EMD. So in this case, we cannot base our diagnostics on the scalar indicator. So we had to choose based on the frequency, the spectrum of the signal, where we have 3 main zones that corresponds to the defect. So an EMD analysis were more chosen with the 3 EMFs, and as we can see in EMF 2, the clear presentation of the rotational frequency FR1 with its harmonics indicating the presence of the defect even in a half extracted tooth. As for the case of the fully extracted tooth, the VMD only needed 2 EMFs to extract the fault characteristics as shown in figure 8. So in conclusion for this part, VMD has proven to be more effective in isolating significant signal components with a reduced number of modes, offering better adaptability and precision in fault detection. However, the optimal selection of number of modes for VMD remains a crucial challenge that requires careful consideration. While VMD generates a larger number of EMFs, it has shown limitations in effectively separating signal components, especially when dealing with subtle faults. Moving on to the next part, in this thesis, we propose a new criterion based on the normalized variation of the Shannon entropy for determining the number of EMFs. The flow chart of the process of determining the optimum number of EMFs is shown in the slide. Starting off with measuring the signal and calculating the Shannon entropy of the signal itself. After that, we initialize VMD parameter with a decomposition set to the maximum, usually for 20 EMFs in the case of rotating machinery. Then we start an iterative decomposition where we compare the normalized Shannon entropy with of two successive EMFs. Once the similarity reach 99%, that means the stopping criterion reach under than 0.01 in two consecutive EMFs, then we chose the optimal number of EMFs. To validate the proposed criterion, we used a sum of sinusoidal signal to, where we know the corresponding number of EMFs beforehand. The criterion shown, the variation of the proposed criterion shows that the value of the EMFs is less than 0.1 for 4 EMFs, resulting in 3 EMFs. After decomposing with the VMD, we obtained the 3 original sinusoidal signals. In this section, we validated the proposed criterion using a simulation of gear faults of the test bench shown in figure 12, using a proper model, mathematical model, and the signal is shown in figure 13, where we have two meshing frequency modulated by the rotational frequency of the supporting shafts. The proposed criterion for this case gave us 4 EMFs for fault detection. The results of the decomposition is shown in figure 15, where we can see the EMFs from 1 to 4 and the corresponding spectrum, as well as the envelope, where we can see that EMF1 and EMF2 have different modulation due to the isolation of both meshing frequency separately. And EMF3, EMF4 shows the combination of rotational frequency 2 and 3 corresponding to the defect, because the meshing frequency collided in these two EMFs. So in a conclusion for this part, the new criterion proved effective in determining the optimal number of EMFs needed for avoiding over and under segmentation. Numerical tests on sinusoidal signals with known components demonstrated the criterion's ability to accurately identify and isolate the original signal constitution. When applied to simulated gear faults, the criterion ensured precise separation of meshing frequencies and fault modulation, thereby enhancing the capability of VMD for targeted fault diagnosis in rotating machinery. Moving on to the fifth part and fourth part, the combination of VMD with wavelet multi-resolution analysis. For this part, a test bench was used, which is locally manufactured in the laboratory of mechanical and structure at the University of Galma. The test bench is consisted of an electric motor, a two-stage gear box, and a brake. The defective gear is shown in the figure, and the corresponding frequency and the characteristics of the gears are shown in the table. 4 signals were chosen for this study, 2 in which are without defect and 2 with defect. These signals were chosen specifically due to the high level of noise contained in both signals, as shown in, for example, S1, where we can see that the kerdosis for a case without defect reaches 5, indicating the high level of noise present in these 4 signals. The mathematical formulation of the wavelet multi-resolution analysis is shown in equations 11 to 13, and the flow chart of the decomposition is shown as well. Starting off with the signal procession without gear defects, that is to say S1 and S2, where we have 2 rotational frequency for both signals. And the use of optimized wavelet multi-resolution analysis itself showed us the presence of the rotational frequency of FR2 and the multiplication of FR1 in S2. The resultant decomposition of using VMD for S1 resulted in 4 EMFs, as for S2 resulted in 3 EMFs. The EMFs isolated perfectly the meshing frequencies and their harmonics. As for the case of S2, we can notice the presence of the FBR, which is the belt resonance frequency proven after calculation. The envelope spectra obtained from wavelet multi-resolution analysis for each EMFs are shown in this slide. For the first case of S1, we can see the presence of a misalignment as shown in EMF4 and EMF1 and EMF2. As for the case of S2, we can see also the presence of the belt frequency, which indicates the presence of the defect in the belt as well, as shown in figure after visual inspection. Moving on to signal processing with gear defect, the two signals S3 and S4 are first analyzed with wavelet multi-resolution analysis, where we had no presence of the modulation of the gear defect frequency. After a decomposition using VMD, same as the old case, for S3, the EMFs resulted were 5, and for S4, the EMFs were 4. As well, the EMFs perfectly isolated the meshing frequencies and some of the harmonics in both cases, plus the belt resonance frequency in S2. The absence of the belt resonance frequency for S1 and S3 is due to its closeness in value to the meshing frequency FM1. So, after applying the wavelet multi-resolution analysis for both cases, we can clearly see the identification of the gear defect in EMF2 for S3 and S4 by the modulation of the rotation frequency of the defected gear. As a conclusion, the EMFs obtained by VMD were processed using wavelet multi-resolution analysis, allowing better isolation of resonance frequencies and identification of fault-specific parameters. The method successfully detected characteristic frequencies associated with gear faults, and this approach offers a promising solution for early and reliable fault diagnosis. Finally, the automatization of fault detection using VMD and long short-term memory neural network. The flow chart of the proposed approach is as follows. Starting off with data acquisition. After that, we have the application of VMD to decompose signals based on the proposed criteria earlier. The EMFs obtained are furthermore subdivided into training set, validation set, and a test set. The training set and validation set are used to obtain the feature matrix, and it will be used to train the LSTM model. The test set is furthermore applied to test the LSTM model and using the classical vibratory analysis of envelope analysis. This slide presents the mathematical foundation for the LSTM and the scalar indicators used to train the model. In the experimental validation of this approach, two different data sets were used. The first one is the LMS data set described earlier. The second one is a well-known data set obtained online with the name Case Western Reserve University bearing data set, containing bearing defects from inner ring, outer ring, ball defect, and cage defect. The corresponding frequency characteristics are shown in both tables for both data sets. And the complete ensemble of the data sets are shown here, where we can see a variety of the defects for both gears and bearings, plus the combination of gears and bearing defects. Starting off with a classical vibratory analysis using envelope analysis and VMD to see the performance of classical methods against advanced signal processing techniques. For most cases, the classical vibratory analysis were not able to detect faults, such is the case for Case Western Reserve University bearing data set, and as well for the case of the LMS data set. The application of the combination of VMD LSTM after obtaining the EMF, we calculate the feature matrix using the scalar indicators shown earlier. After that, we train the recursive neural networks, starting off with neural networks to identify the defect type, whether it was a healthy bearing, a ball defect, an inner ring defect, or an outer ring defect. After that, RNN2, RNN3, and RNN4 are used to identify the severity of the defect, whether it's small, average, or critical. And to furthermore see the limitation of our approach, an RNN5 was trained to see the combination of all the defects together. The training progress of RNN1, for example, is shown in figure 25. We can see that a strong correlation between the training and the loss and the validation segments, as well as the validation reached 100% and the loss reached 0% in both cases. The confusion matrix for RNN1 is shown in figure 30, where we can see we reached 100% classification for the case of defect type detection. The rest of the RNNs, the RNNs is shown in figure 31. We can see that for the defect type and defect severity, all classification reached 100% accuracy. For the case of the second data set using the LMS test bench, RNN6 was as well trained to see the defect type, whether it was healthy, a bearing defect, a gear defect, or the combination of bearing and gear defect, followed by RNN7 and RNN8 to see the severity of the defect in bearings and in gears. Finally, RNN9 was trained to see the combination of gears and bearing defects. In the same way, the training progress also agrees with accuracy and loss, and the confusion matrix resulted from RNN6 is shown 100% accuracy in diagnosing the defect type. The rest of the RNNs is shown in figure 34, where we can see 100% classification for bearing defect severity and gear defect severity, and only the case of combination of gears and bearings were 83.3%. This is due to the nature of gears and bearing defects that are similar and cannot be diagnosed using a scalar indicator and needs further investigation. To summarize, this table compares classical vibratory analysis and the VMD LSTM approach. While vibratory analysis failed to detect ball defects and all the defects present in the LMS test bench, the proposed approach accurately detected all the defects except the combination of gears and bearings. And to see the performance evaluation of the proposed approach using the same number of elements for the training and validation, we can see that the proposed approach overlaps all other approaches such as the MLP, the 1D CNN, the 2D CNN, and regular LSTM for both cases. Finally, this method, as a conclusion, this work developed a novel hybrid method combining VMD and LSTM neural networks, leveraging the adaptive signal decomposition capability of VMD and the temporal learning strength of LSTM. Targeted fault detection in gears and bearings of rotating machinery and validated on two separate data sets achieved better performance than the classical vibration analysis method and enable precise and accurate classification across various fault types and severity levels. As we reach the final section of our presentation, let's take a moment to reflect on the key takeaways of the path forward. This thesis aimed to design diagnostic techniques tailored for rotating machinery using advanced signal processing while tackling key challenges in fault detection such as non-linearity and signal noise and overlapping defect signatures. Compared EMD and the VMD method, highlighting VMD's superiority in isolating EMFs relevant for fault diagnosis. Introduced a novel Shannon entropy-based criterion to optimize the number of modes in VMD, and combined VMD with wavelet multi-resolution analysis to enhance detection of gear defects under noisy conditions. Finally, I developed a VMD LSTM model enabling automatic detection and classification of faults in bearings and gears. As for the future perspective, the development of additional indicators for multi-fault diagnosis in high noisy environments, the optimization of decomposition technique using hybrid approach to maximize the accuracy of vibration monitoring techniques, the expansion of experimental tests to include signal simulating various degradation levels, ensuring the practical applicability of the proposed diagnostic models in industrial settings. The main findings of this thesis were published in a Class A journal in two different articles. The first one entitled Diagnosis of Faults Using a New VMD WVMRI Approach Optimized by New Criterion Industrial Application, and the second one entitled Robust Fault Detection and Severity Classification in Rotating Machinery Using VMD LSTM for Limited Data Scenario, as well as the participation of national and international communication. And thank you for your attention.